Hi, today we're going to go over our Exam 3 study guide. And there are topics on here including VSEPR, geometry, the polarity of molecules, chemical and physical properties and the changes that we can identify in Chapter 7, balanced chemical equations, stoichiometry, limiting reactants, and percent yield. Our first topic that we're going to cover is VSEPR geometries. So let's begin by defining what VSEPR is. VSEPR is valence shell electron repulsion theory. And what VSEPR does, the models that we create, we're looking at a central atom and how we can distribute electron density about that central atom. And the electron densities that we're going to look at can either be regions of where we're having bonded electron pairs around that atom or lone pairs of electrons. And we're going to create, first of all, in our examples, what we call an electron domain geometry. An electron domain geometry accounts for the distribution of regions of electron density about a central atom. And we described 5 basic geometries to maximize distances between regions of electron density to minimize the repulsive interactions that these negatively charged regions have. Second, we're going to look at molecular geometries. And what we're going to show is that a molecular geometry is the same as the electron domain geometry if the central atom doesn't have a lone pair of electrons. If the central atom does have a lone pair of electrons, the molecular geometry is derived from the electron domain geometry. And we'll go over specific examples of that. The final topic we're going to look at is predicting if a compound, a molecule, is polar or nonpolar. And this is reflected in what we call a dipole moment or lack of a dipole moment. Dipole moment is a vector quantity, and we're going to show that vectors have both magnitude and direction. So 2 features that we look at when we determine if a molecule is polar or nonpolar are electronegativity differences between atoms involved and the geometry. So that gives the differences in electronegativity. Well, that's the magnitude of our vector. The shape of the molecule gives us the directionality of the particular vector. And those are 2 features that we're going to be looking at in some of the examples that we'll discuss. The first example that we're going to look at is carbon tetrachloride. And we're going to answer these questions that we just showed here. Carbon tetrachloride, it's going to be a central carbon atom surrounded by 4-chlorine. And so when we want to answer these questions that we're commonly approached with in VSEPR, the first thing we need to do is to write a Lewis structure for a particular molecule. So one thing we do is we write a valence electron account. And let's do that. Carbon has 4 valence electrons. And there are 4 chlorine with 7 valence electrons each. And this valence electron account, this tells us the number of electrons that we're working with when we're building a Lewis structure. We have a central carbon, and we're surrounded by 4 chlorine. So we need to at least have single bonds to our chlorine atoms. And up to this point, we've used 8 electrons. And now let's fulfill the octets of our surrounding atoms. And we would see that we've used up all of our electrons that we have available to us. So let's first of all describe the electron domain geometry and recognize that this molecule fits the model A, a central atom surrounded by 4 atoms, we'll call those B, and our central atom doesn't have any lone pairs of electrons on it. So in this case, we would see that the best way to distribute electron density around our central carbon atom is in a tetrahedron type of arrangement. A tetrahedron, by convention, we use our straight lines representing atoms or regions of electron density that are in the plane of the dry erase board. In this case, the wedged line represents regions behind the board, or out of the board, I'm sorry. The dashed line are the regions behind the board. Now, in this case, and this would give us our electron domain geometry, all these regions around the central carbon atom are what we call electron domains. There are 4 electron domains about the central carbon, and this tells us that our electron domain geometry is tetrahedral. Okay, now for carbon tetrachloride, all of our electron domains are involved in bonding. There are no lone pairs of electrons. Let's put our chlorine around our central carbon. I'm not going to put lone pair of electrons just so we can visually look at this a little easier. Now, notice our molecular geometry will be identical to our electron domain geometry because for this situation, there are no lone pair of electrons on the central carbon atom. And this would be true for any situation in which a central atom does not have lone pairs of electrons. A tetrahedron, if we want to think of it using a model, and these models can be purchased probably through Amazon, we would have a central carbon, and these would represent the 4 different chlorines that surround it. They're symmetrical, they're at 109.5 degrees, and that's a best way to maximize the distribution of electron density about our central atom. So the third question we're going to answer is regarding the polar or nonpolar nature of this type of molecule. Now, what's big in this example, symmetry. Symmetry is very important. Symmetry is one thing we look for. And again, another important factor here, differences in electronegativity. So let's remember from an earlier chapter, carbon is less electronegative than chlorine. So what happens in this situation is chlorine pulls electron density away from the central carbon atom. I'm going to use an arrow to help show how electron density is drawn away from the central carbon atom. Now, remember, this is very symmetric. if these are all chlorine atoms, well, the electron density is being pulled equally in this direction, and that's at 109.5 degrees, equally in that direction, and that's also at 109.5, and so forth. Notice there's no net distribution of electron density because it's being pulled equally in all directions about that central carbon atom. In other words, if we look at how these arrows are distributed symmetrically about our carbon, we would see that there is no net dipole moment. Vector addition is very important. The vectors cancel out. This nonpolar for this particular example. Let's move to our second molecule, because the second molecule that we're going to look at, very similar to carbon tetrachloride. It's just a little bit different. Let's leave this structure here. I'm going to leave the chlorine on there. And we're going to look at another organic molecule that's very similar to carbon tetrachloride. In the description, this is methyl chloride. I told you in this description, carbon sits in the center. Here's carbon. And it's surrounded by 3 hydrogen and 1 chlorine. There's the molecule that we're thinking about. And let's think about our questions that we were asking earlier. Is the molecule, let's look at the electron domain geometry. Just like carbon tetrachloride, this is again a central atom that has 4 regions of electron density about it. It's AB4. There are no lone pair of electrons on the central atom. So once again, the electron domain geometry is tetrahedral, and our molecular geometry is still tetrahedral. As of right now, this molecule shares the geometry similarities between carbon tetrachloride that we discussed a few minutes ago. Same, tetrahedral, tetrahedral. But now we have some differences in terms of polarity or non-polarity. So let's think about distribution of electron density. Chlorine is very electronegative. It's a halogen. It sits on the far right-hand side of our periodic table. And what we would recognize is that electron density is pulled quite favorably in the direction of our chlorine, and carbon is just a little more electronegative than hydrogen. So electron density is being pushed in this direction. But what's really big here is the lack of symmetry. Carbon tetrachloride, symmetric distribution of differences in electronegativity in comparison to our central atom. In this case, we don't have a symmetric situation. There is a net distribution of electron density that favors the direction of where our chlorine sits. And we would see that there's a slight region of negative charge separation towards the end of our chlorine part of our molecule, and a little less electron density towards the bottom of the molecule. And what we end up with, the difference here, is this CH3Cl does experience a net dipole moment. Since it experiences a net dipole moment, there is a net distribution of electron density in the direction of our chlorine. This is polar. the really big underlying way to identify it is how non-symmetric it is. Remember, if all of these atoms were the same that surround the central atom, we're going to get a non-polar situation. One of these atoms are different. There's going to be a distribution of electron density that's going to be slightly different in one direction in comparison to another. This particular molecule, polar. Let's move to another molecule. Selenium tetrafluoride. So when we begin discussing this molecule, we're going to answer our questions that we asked before. We're going to ask what the electron domain geometry is. What's the molecular geometry? Is the molecule polar or nonpolar? So when we ask questions regarding VSEPR, we begin by writing a Lewis structure. Our steps include taking account of the number of valence electrons we have available, we have 34 valence electrons, writing a skeletal structure, putting in bonds to our surrounding fluorine atoms, and then fulfilling the octets of the surrounding fluorine. And we would see at this point, we've used up 32 electrons, and there are 2 electrons remaining. Now, selenium is in period 3 or beyond, and selenium can experience an expanded octet. The 2 extra electrons will be placed on the central selenium atom. And now we can answer some questions about selenium tetrafluoride. First question is, what's the electron domain geometry? In other words, how many regions of electron density are about the central selenium atom? So notice there's 1, 2, 3, 4. There are 4 bonding regions, and there's 1 region of lone pair of electrons. We have 5 regions of electron density about the central selenium atom. How can we maximally distribute electron density about our central selenium atom? The geometry that we introduced earlier, when we have 5 regions, we can put 3 regions in the plane of our dry erase board, 1 region behind the board, and 1 region coming out. And the electron domain geometry represents regions of electron density around our central atom. 4 of them are involved in bonding, and we also have a lone pair. And that's how we would distribute electron density about our central atom. And the geometry for the electron domain is going to be trigonal bipyramidal. I have a 3-dimensional structure here to show you. This is a trigonal bipyramidal type of geometry. Notice we have electron density above and below, and we have 3 regions along the equatorial plane. Think of this as the planet Earth. These would represent the equator. These 2 regions represent the axis. And for right now, let's just assume that these spheres surrounding it are just regions of electron density, just for the time being. So there are the three around it. And they make up a trigonal base around the equator. And we can think of these as creating a pyramid. And there's one above and below the molecule. So what we call it is trigonal bipyramidal. And that's our electron domain geometry. That would be our electron domain geometry. And that's the best way to distribute. We have three regions that are 120 degrees around our axis. And then these equatorial are around the equator. And then the axial are at 180 between each other and 90 between each of those regions that are around the equator of the molecule. So that's trigonal bipyramidal, the electron domain geometry. So now what we're going to do is we're going to place our atoms on there and put one lone pair of electron in one position. Where are they going to occupy? Because in this situation, we do have to make a decision. We have to decide, should we put a lone pair along the axis, or is it more beneficial to place it along the equator of the molecule? Now, energetically speaking, the best place to put a lone pair of electrons where it would occupy, well, if we put them along the axis, well, now this region that would have a lone pair interact 90 degrees between these regions along the equator. If we decide that, hey, let's put them along the equator, now this lone pair interacts only at two positions at 90 degrees along these axial regions. And what we find out experimentally that are energetically the best is to place a lone pair of electrons along an equatorial position. So all lone pairs will be placed at equatorial positions when we're deriving a molecular geometry from a trigonal bipyramidal electron domain geometry. So this is where our lone pair of electrons go, and we end up with a structure that's called a seesaw or a sawhorse. Notice it would look like that. You have these two that go up and down, then you have those two out there. And that's a seesaw molecular geometry in this particular example. So this is where we put our fluorine. One up here, one behind the plane, and one out there. And we're going to just, by convention to show it, put a lone pair of electrons there. And the molecular geometry is seesaw. So let's now ask our final question. Is the molecule polar or nonpolar? Now, I did go over a rule that we should address is when we have a lone pair of electrons, a single lone pair, we're going to get a molecule that's going to be polar. Let's show why. Fluorine is the most electronegative atom. And fluorine is going to pull electron density below the plane of the molecule and above the plane of the molecule. And these two are going to cancel one another. However, around the equatorial axis, we're going to see that electron density gets pulled unequally around the equatorial region, and we're going to end up with a net dipole moment. And what we're going to see is that for this molecule, we are polar. And it's due to the fact that there's an unequal distribution of electron density around the equatorial position of this particular molecule. So this is polar. Let's move to our final two molecules for today. Carbon dioxide is one molecule that we did spend some time earlier. CO2. And we did draw the Lewis structure for this. And we would see that we have a central atom surrounded by two atoms. And this follows as an AB2 type of molecule. Now, in this case, since there's two regions of electron density about a central atom, and there are no lone pairs of electrons, then what we were going to find out is that our electron domain geometry, linear, is the best way to distribute regions of electron density around our central atom such that they're 180 degrees apart. And since there are no lone pairs of electrons on the central atom, the electron domain geometry and the molecular geometry are the same. Linear. It's a linear molecule. It has a linear electron domain geometry and a linear VSEPR predicted structure. Now the next question, is it polar or nonpolar? Oxygen is more electronegative than carbon. Oxygen pulls electron density to the left, to the right, and it pulls it equally in an opposite direction to the left. Now notice this equal pull of electron density in opposite directions cancels the net dipole out, and we end up with no net dipole moment. And we would say that carbon dioxide is nonpolar. And we can see how those arrows point in opposite directions and would cancel one another, and we would end up with no net distribution of electron density in one direction or the other, and we end up with a nonpolar molecule. Let's move to another geometry, another formula that has the same type of formula but a different geometry, and we're going to find out it's going to be polar. We're going to look at sulfur difluoride. It has a very similar formula. One atom surrounded by two other, but the way to think about it in terms of describing it, we would have to go through writing a Lewis structure, assigning an electron domain geometry, and then seeing how we would derive a molecular geometry from our electron domain geometry. Let's go through those steps. We would write the Lewis structure by taking account our valence electrons. Sulfur has 6. And there are 2 fluorine, 7 each. And we would have 20 electrons to work with. So we have a central sulfur, 2 fluorine, and then we would fulfill the octets of our fluorine. And we would see that we've used up 16 electrons, and we have 4 electrons remaining. And those 4 electrons we would place on our central sulfur atom. So the first question we're going to ask, What's the electron domain geometry about the central sulfur atom? We have a central sulfur. And how many regions of electron density about it? 1, 2, 2 involved in bonding, and 2 lone pair. 4 regions of electron density. How can we maximize the distance of electron density about a central atom when there's 4 regions about it? Well, remember, tetrahedral is the best way to maximize the distance between these regions of electrons. So the electron domain geometry is tetrahedral. Now let's place the fluorine in this model right here. And just so we can see it easier, we can put them here where these straight lines in the board are. I could have put them anywhere else. Remember, they're all arranged about 109.5 for the time being. And we're not going to put lone pair of electrons just so we can see it easier. Now, when we look at sulfur difluoride, how it's derived from a tetrahedral geometry, we only see the sulfur and the 2 fluorines. We don't see electrons. They're too small. So we don't see these regions. And if we turn this in another direction, we would see that we have a central sulfur surrounded by 2 fluorine. And we would say that this molecular geometry is bent. Notice it's derived from an electron domain geometry that's tetrahedral. Let's just take these 2 regions off where there's lone pair of electrons, and we would end up with a bent structure. Now, we said earlier that if it was tetrahedral and they were all involved in bonding, all of the bond angles would be 109.5 degrees. Now, the lone pair of electrons that sit up in this region, they would cause these 2 regions below it to compress a little bit, and these bond angles would be a little less than 109.5. Now, the next question we're going to ask, is the molecule polar or nonpolar? And when we decide in this case as to whether a molecule is polar or nonpolar, we think of two things as we've been going through. First of all, differences in electronegativities between the atoms involved in bonding. Fluorine is the most electronegative atom, and we would see that it pulls electron density in that direction, and it also pulls electron density in that direction. And what we would recognize is that this molecule has a net distribution of electron density, and we can use vectors. We can draw these as vectors because these have direction and position. What we would do is we would connect these arrows. This is actually how we draw vectors. And we draw what we call a resulting vector. You don't need to do this on an exam, but just in case you were wondering where this comes from, now, what this tells us is that the differences in electronegativity point in a region above the sulfur atom because the electronegativity of the fluorine is so great that it pulls electron density in that direction. And we end up with a region of slight negative charge up here where our fluorines are at, and a region that's a little less electronegative on the bottom of the atom. And we would see that this does have a net dipole moment. And unlike carbon dioxide that was linear, this molecule, sulfur difluoride, is polar. So those are the topics in chapter 5. I think that covers a lot of them that we were discussing. Let's move into chapter 7. Chapter 7 began by discussing chemical changes that occur. And one aspect of chemical reactivity and understanding about chemical reactions is a balanced chemical equation, because there is a law we have to abide by, and that is the law of conservation of mass. We can't have more atoms on one side of a chemical equation than we have on our product side. And we're going to go through a strategy for balancing a chemical equation that I discussed a little bit earlier. Now, for situations in which we have organic compounds, we're going to go over how to balance a chemical equation. And what we're going to show is that